आइए समझते हैं। Welcome back to the explainer. Today we're taking complex tech and making it crystal clear. We are going to completely level up your LangGraph AI agents and give them some incredible new abilities. I'm talking about giving them real conversational memory, the superpower to literally freeze time for human supervision, and this is the crazy part, the magic to completely alter an AI's thought process right in the middle of an action. Let's get into it.
Here is our quick roadmap for today. Number 1, adding memory to chatbots. Number 2, freezing time before action. Number 3, updating the agent's state. And finally, number 4, how message reducers actually work.
All right, Section 1, adding memory to chatbots. Okay, let's dive into this, because it solves a huge problem.
Have you ever noticed that out-of-the-box AI agents have, terrible amnesia? Think about the contrast here. With a basic, stateless bot, you could tell it your name is Junaid, and literally a second later, you ask it your name, and it has absolutely no idea who you are. The whole history just, poof, vanishes into the void. But what we really want is a stateful agent. An agent that maintains a continuous session, one that remembers exactly what you discussed yesterday or even last week. Well, LangGraph actually gives us this brilliant built-in solution for this exact amnesia problem. It's called Memory Saver. So think of Memory Saver like a checkpointer. It's basically an object that persistently saves your entire conversation history straight to a database. Now, that could be just a simple in-memory dictionary if you're just testing things out, or a full-blown, robust database like Postgres or MongoDB if you're pushing to production. All you do is initialize this Memory Saver object and pass it right in when you compile your LangGraph. Super simple. So how does it actually keep all those memories organized? It uses threading. This checkpointer groups all your messages into one single conversation and slaps a unique thread_ID on it. Then, when you want to chat with the bot, you just pass that specific thread_ID inside your graph's configuration, and the magic happens behind the scenes. The LangGraph agent automatically pulls up that complete history. So when you ask, "Hey, what is my name?" the agent instantly checks that thread, spots the earlier message, and says, "Your name is Junaid." Section 2, freezing time before action. Now that our agent can remember things, we really need to set some boundaries. We're moving to an incredible capability, stepping in and freezing time before the AI does something permanent. I want you to imagine this for a second. You've built this highly capable autonomous AI agent. It's allowed to use tools, make its own decisions, and execute actions. But what happens if the AI decides to make a critical mistake? What if the action it's about to take is totally irreversible? The source material actually paints a really vivid picture of these high-stakes scenarios. Think about, say, a military drone operating at a border that misidentifies a friendly target, or picture an automated banking AI that's about to instantly transfer funds for a completely terrible loan. In those situations, letting the AI just act entirely on its own, no way. That is incredibly dangerous. Human oversight there isn't just a nice-to-have, it is absolutely mandatory. To solve this, LangGraph gives us this powerful, almost magical feature called interrupt before. Basically, when you're compiling your graph, you can pass in this argument along with the name of a specific node, like your tools node. It's literally like a hero in a movie snapping their fingers to freeze time right before a disaster strikes. The graph runs perfectly up until that exact node, and then it just stops. It waits there in suspended animation. And this brilliantly illustrates the complete human-in-the-loop workflow in 4 easy steps. Step 1, the agent decides it needs to use a tool, maybe to make a payment. Step 2, graph execution freezes instantly because of that interrupt before command. Step 3, a human operator gets a ping, reviews what the AI is about to do, and decides whether to approve, reject, or modify it. And finally, step 4, the human gives the signal. The graph unfreezes, and it completes the action safely. The human acts as the ultimate safety net here. Which brings us to Section 3, updating the agent's state. Because here is where things get truly fascinating. See, while time is frozen, the human operator doesn't just have to sit there passively watching. They literally have the power to alter reality before the AI proceeds. We do this using 2 incredibly powerful methods, get state and update state. When the graph is paused, you use get state to pull an exact snapshot, like a photograph, of exactly what the AI is thinking and what tool it plans to use. And if you don't like what you see, you use update state to securely inject your own modifications. You're effectively changing the AI's mind before it acts. Let's break down the actual technical steps to make this happen. because it's a real game changer. First, you grab that current snapshot using get_state. Next, you copy the exact AI message that contains the tool call you want to fix. Then you modify the specific text of the query to make it better. And listen, this is the absolutely crucial trick here. You must keep the exact same message ID from the original AI message. Finally, you just send that new, improved message back into the graph using update state. To put that into perspective, let's look at a specific example from the source. The AI decides it wants to search the internet for just the single word LangGraph. The human looks at that frozen snapshot and thinks, wow, that is way too generic. So the human intercepts the message, changes the search query to LangGraph human-in-the-loop workflow, and pushes it right back into the system. And the best part? The tool never even knows that original generic query existed. All right, section 4, how message reducers work. So the crucial point here is, how does the system actually know to overwrite the old message instead of just adding a second one alongside it? To explain the deep technical mechanics of this without breaking the graph, the source uses this absolutely brilliant analogy. Think of your graph state as a refrigerator, and the conversation messages, those are eggs going into the fridge. Now, standing right in front of that fridge is a manager, which LangGraph calls a reducer function. This reducer's entire job is to look at the eggs and decide exactly how they get placed inside. So here's the rule the reducer follows. If you hand it an egg, a message with a brand new ID, the reducer just appends it. It puts a new egg in the fridge. But if you hand the reducer an egg that has the exact same ID as one that is already sitting in the fridge, the reducer does something totally different. It takes the old egg out, tosses it, and replaces it with your new one, a complete swap. And that right there is exactly why keeping that identical message ID was our secret trick just a minute ago. By passing the same ID, the reducer replaces the AI's bad query with our awesome one. This prevents duplicate queries from running, it keeps your entire conversation history perfectly clean, and it guarantees that the tool only ever sees the human-modified query. It's an incredibly elegant system. And this brilliantly illustrates our final step. Once we've updated the state and swapped that message, we gotta get time moving again, right? To unfreeze the graph, you simply pass the word none as the input to your stream, along with your thread ID configuration. This acts as a signal, telling the graph to wake up and resume from exactly where it paused. But now, it's armed with our perfectly altered query. So, think about what we've accomplished today. You've now given your LangGraph AI the memory to hold continuous, long conversations, the ultimate safety net of freezing time, and the flexibility of on-the-fly human corrections. Now that you have this total control over your agent's actions, what critical, high-stakes tasks will your AI automate safely? Something to really think about. Keep exploring, and thanks for joining me for this explainer.